So this is the place where we had stopped in the last session, that we had created a model in Etabs software. So can anybody tell me the full form of Etabs? What is the full form of Etabs? We had created a 7-story building. We had seen the material property, defined the material sections. So frame sections were the beam, column, and slab. We had defined that. We created 7-story building with spacing of 6 meter in X direction, center to center, and spacing of 5 meter in Y direction, center to center. So height of the building is 21.2 meter. In X direction, it is 24 meter, and in Y direction, it is 20 meters. Okay, so that is the basic dimension of our building. So the full form of Etabs, just hold on.
Extended three-dimensional analysis of building structure, sir, I think.
Yeah, so it is extended 3-dimensional analysis of the buildings. So this software is made with the purpose for buildings only. Okay, so any type of building analysis, it is very convenient to do it because it has all the built-in options. CSI has many products. The CSI SAP 2000 is more accurate than ETABS as it is fully FEM based software. So ETABS is not a fully FEM based software because in fully FEM based software you cannot define a rigid diaphragm. So defining a rigid diaphragm is very important. If I show you the elevation, so here at all stories you can see this pink, right? Pink lines. So these represent the story level. So at each story we have a mass. Okay, and if we consider this uh, diaphragm means your slab plus the beam. Okay, so both are part of the diaphragm. So if we consider this element to be rigid, so if pink elements are rigid, that means your building has only one degree of freedom. So it can move only in one direction, that is lateral direction. So our analysis becomes simple. Now, if the this pink element is not a rigid diaphragm, if it is a flexible diaphragm, then it becomes a 3 degree of freedom. Okay, so your analysis becomes more complex and you cannot solve it manually. So manual analysis can be done when the diaphragm is rigid. And when diaphragm is rigid, we call it a lump mass modeling. So we are lumping the mass at each story. So that is called a lumped mass modeling, LUMPED, lumped mass modeling. So that is how it is represented as. Okay, so lump mass modeling is simple, and we can do static analysis, we can do dynamic analysis in software as well as manually. So that is our target today, that using the lump mass model, we will be doing the analysis using static method and response spectrum method in ETABS. So lump mass model, that means your mass at each story is lumped. You calculate the story mass. Okay, so at each story you calculate the mass, and then suppose story 1 is there, we call it M1, mass of story 1, mass of story 2 M2, M3, M4, M5, M6, M7. So your you will calculate 7 masses at each story and you will create a mass matrix. Okay, so because the solution is in matrix form for dynamic analysis. Okay, for static analysis, it will be just calculation of the weight at each of the story. For dynamic analysis, you have to create the matrix. So we will create a mass matrix. Okay, we will see it later. Just remember right now. So at each story, you calculate the mass. For static analysis, use those mass as a weight. And for dynamic analysis, create a mass matrix. That is how we do it. So for response spectrum method, you will have to create a mass matrix. Okay, so now once that is done, in lump mass model, the mass at the story level is uh, rigid. Okay, so we call it a rigid diaphragm. So we assign a rigid diaphragm. We had seen in definition. that rigid diaphragm can be assigned. Okay, so now if diaphragm is rigid, that means we can do a lump mass modeling. Okay, so your building can move only in one direction. So your analysis becomes simple and you can manually solve the problem. If it is semi-rigid, you cannot solve the problem manually. You have to depend on software. So to solve it manually we consider diaphragm to be rigid. So slab and beam, the bending moment will be zero. Okay, so in lateral direction only. So it will transfer your, what is the purpose of diaphragm? Diaphragm means if you see this 3D figure, diaphragm is your slab. Okay, so slab is the mass in your whole building. So on this floor, this is the mass that we will be considering of the slabs, right? So now when we consider mass at this level, you know force is mass into acceleration, right? So that's why we are calculating the mass. So once we calculate the mass of at this floor level, mass into acceleration will give us the force. So that is part of the lump mass model because total mass we calculate. In semi-rigid diaphragm, this is not possible. Okay, and uh, why we are doing this force calculation? Because it has an inertia. So inertia is generated due to the mass only. So force is mass into acceleration because we follow the law of inertia. So inertial force is mass into acceleration, and that you will calculate based on your any code. If you are doing static method of analysis, it will be weight into the acceleration only. Okay, so that is the first part, that is estimation of the story weight. Whenever you do estimation of the story weight, the software will calculate it automatically, but you need to create an Excel, and in Excel you need to estimate the story forces. To estimate the story forces, you need to calculate the story level masses. Okay, so that is the prime requirement for creating an Excel, and rest in software it does it automatically. So what is happening when these slabs are rigid diaphragm, all the force will be generated at center of mass. Okay, there will be center of mass and there will be center of rigidity. So center of mass is the location where mass of the floor is concentrated. Okay, mass of the floor, not the building, only the floor. So at each floor you will have a center of mass. So center of mass is the position where mass is concentrated. Center of rigidity is the position where stiffness of your floor is concentrated. Okay, not the building, stiffness of your floor is concentrated. So you will get center of mass, you will get center of rigidity. When you are doing manual calculation, software does it automatically. And your force will be, earthquake force will be created at center of mass. That we will see after the analysis. Now this force will be distributed to the columns because now force is acting at only one point. Let's say this is the center. So your force is acting at this point, earthquake force on story 7. But there are so many columns, so that force needs to be distributed. So with rigid diaphragm, what is happening based on the stiffness of the each of the columns, okay, the force gets distributed. Okay, so that is how we are able to do it manually, and then software redistributes based on the stiffness of the each of the columns. But in when you give a semi-rigid diaphragm, the solution becomes difficult. So we cannot do it manually. We have to follow the tributary path, so that becomes complicated. Right now we will see only that part, that how lump mass modeling is done, because we have a slab of 125 mm which is rigid, and hence we have given it as a rigid diaphragm. So I will assign right now a rigid diaphragm to all these slabs. So I will first select the object type, and it is floors. I will select all the floors. I will assign uh, in shell element. Okay, so whenever you will be looking at the slab or the wall, okay, so that are wall and slab are under shell element. So whatever definition you will be doing for them or assigning for them, it is part of the shell element. So that option will be available only in the shell. Okay, so here diaphragm is there, select the diaphragm. D1 diaphragm you had defined as rigid. Now I will apply. Okay, apply and okay. So now you can see that whole of the uh, center, this force will be generated at this point only. So that is the location of center of mass right now. So diaphragm, when we assign it, calculates the center of mass. Okay, so at this position, your earthquake force will be assigned in your building. So that is center of mass. Center of rigidity will depend upon the stiffness of your vertical elements. So vertical elements are what? Either the columns or the shear wall, so or the infill wall. So all those are vertical elements. So based on the stiffness of the vertical elements, center of rigidity will get calculated. We have a separate session on that, how to manually do that. Okay, right now we will see in software. Okay, so this is very important step, you cannot miss this. So you have to assign it the all the floor levels as the rigid diaphragm if it is a rigid diaphragm, or a semi-rigid diaphragm if it is a semi-rigid diaphragm. So your definition of diaphragm is very important. Okay, you cannot forget it is a semi-rigid or a rigid. You need to provide the definition and then assign it in your building. Okay, so now let's see this concept in a theory form. Okay, so what we have done it in the software, let's see it in theory form, because this is part of the dynamics. Okay, so we are going into dynamics right now. Okay, so why multi degree of freedom? Because if there is only a portal frame, then there is only one mass. Okay, simple portal frame, there will be only one slab level. So one slab level, that means that there is only one mass. If there are 7 story in the building, then there is 7 degree of freedom. Okay, so that is a that is why we call it a multi degree of freedom system. That is more than one is multi degree of freedom system. So if it is only a ground story, then it is a single degree of freedom, SDOF. Okay, if it is a multi-story, then it is a MDOF. Okay, multi-degree of freedom system. So we are generally dealing in high rises, then that is a multi-degree of freedom system. If it is only single floor, then it is single degree of freedom system. Okay, that we will see how to analyze it. So if you will see any dynamics textbook, they will start with single degree of freedom and then with multi-degree of freedom. Our building is a multi-degree of freedom. Concept remains the almost the same. Okay, so you can see mass m1, mass m2, mass m3, or 1, 2, 3 and 4. Okay, 4 masses are there, so this means a 4-story building. Our building is a 7-story, so there will be 7 masses. Okay, so mass m1, m2, m3, m4, m5, m6, m7. So how many stories are there? That many masses you need to assign it here. This is the mathematical representation of your building. So in software, whatever you are doing, when you are calculating it manually using lumped mass model, I repeat again, when you are using a lumped mass model, this is the mathematical representation of that. Okay, so this is the stories M1, M2, M3, M4 story mass that you had calculated. See, mass is all these masses are in kg unit.
Sir,
Hello, hello.
sir, your screen is not visible, sir.
Okay, screen is not visible. Just hold on. Now it is visible.
Yeah, sir.
Okay. So here you can see that multi-degree of freedom system. That means that any building that has more than 1 story, then it is called multi-degree of freedom system. And when you see a dynamics textbook, it will be representing the building in mathematical form. So we call it a mathematical modeling. Okay, so mathematical modeling is representation of building for manual analysis. Okay, and same the software will also be doing, and we will check the manual results with the software results. So by the technical definition, it is called mathematical modeling, because whatever the real structure is on ground, we are recreating in the software and also recreating on our paper for manual calculation. So that is called a mathematical modeling. So mathematical modeling relates to each of the elements should be identified, whether it is a mass element or whether it is a stiffness element or whether it is a damping element. Okay, three type of elements can be there in our building, whether it is a mass element or it is a stiffness element or it is a damping element. So damping element will come when we are providing the dampers. Okay, vibration control dampers we are providing, then damping element will come. Otherwise in routine buildings it is mass element and the stiffness element. Mass element is at the floor level. Okay, so M1, M2, M3, M4, M5, M6 and M7. So 7 stories are there, 7 masses you will calculate at floor level. So that is represented here. Okay, mass M1, M2, M3, M4, M5, M6, M7. So you can extend this diagram up to M7. Okay, so seven masses we have. So your mathematical diagram will have 7 masses, and your stiffness will be the columns. So the stiffness element is either the column or the shear wall. So you need to calculate the stiffness at each floor. Suppose there are 10 columns, calculate the stiffness of all 10 columns. Okay, of your particular floor. So at ground floor, if you have 10 columns, your total stiffness of ground floor is stiffness of 10 columns that you will provide as K1. Okay, so K1 represents right now all the stiffness of the vertical elements in the ground story. So vertical elements means your columns, shear wall and the infill wall. So all three are vertical elements. So if all three are present in your story, all three stiffness needs to be calculated, and it is K1 at ground story, K2 at first story, K3 at second story, and similarly as you progress up to the seventh story, you will have K7, that is the stiffness of the seventh story. Okay, so you have 7 masses, you have 7 stiffnesses in your building, right? So that is what you need to first calculate if you want to do it manually for the dynamic analysis of the building. Clear? So in Excel, you need to first calculate the masses and then the stiffness of all story of your building. So that is the first step to be done. And this is called the mathematical representation of your building. Okay, and software also is following this model only. So if you see it clearly, it is a stiffness is represented by K, mass is represented by M, and damping is represented by C. So right now we don't have a damper in our building, so we will not be having a C matrix. We will be having a mass matrix and we will be having a stiffness matrix in our for the solution of our building for dynamic analysis, that is response spectrum method of analysis. Okay, so we are currently in dynamics, so I will not talk much about response spectrum. We will see the code for response spectrum. So for our undamped system, undamped means there is no damper. So for undamped system, your C matrix will not be there. Only mass matrix and stiffness matrix will be there. So for first story, it is M11, then it is M12. So this is a different type of matrix. Generally, we have a diagonal matrix in this, where only in diagonal we have the 7 masses. Okay, so that we'll see when we will see in the Excel. Okay, and in the stiffness element, we need to generate it as per your particular case. So let's move forward. So, but you have to calculate the mass and then the stiffness so that those values can be used to generate a matrix. And this is your equation of motion for free vibration. So mx double dot, x double dot, that means acceleration. So mass into acceleration, mx double dot, plus k into x, that is stiffness into displacement, is equal to 0. So when it is equal to 0, that means it is a free vibration. Force is not acting. You just want to estimate the basic fundamental characteristics of the system. Okay, so you excite it initially, okay, and then leave it to vibrate on its own. So no external force is applied for the vibration of the building. So the building will vibrate as per its fundamental properties. So that's why it is very much important. And this is what we do for calculating the time period of the building. Okay, in each mode that we'll see what mode is. Okay, so that is very important deduction, that eigenvalue solution we do using this formula only. Okay, you need to manually do this to get the answer. So if you have a damped system, right? So damped system means a damper is provided in the building. That means you will be adding a damping matrix in your equation. So mx double dot plus damping matrix c into velocity x dot. So it is acceleration, velocity, displacement. So mass into acceleration, damping into velocity plus stiffness into displacement is equal to 0. Okay, so your damping is always related to velocity of the system. So that's why if the building is sensitive to velocity, we provide it the dampers. Okay, so that will be more effective. So that is a advanced part. Right now we need to remember only mx double dot plus kx equal to 0. So this is your behavior of the building. Okay, so when we see the behavior of the building, this is a G+2 building. Okay, so there are 1, 2, and 3 floors are there in this building. So when there are 3 floors, there will be 3 into minimum 3 modes of vibration. Okay, so modes of vibration depend upon each floor. There will be 3. Okay, so when you are using Etabs, you have to remember for each floor I need to give 3 modes of vibration. So if you calculate, the software will ask you how many modes the software should calculate it. So if you have a 60-story building, so 60 into 3, 180 modes you need to give input to the software. So for each story, 3 degree of freedom you need to assign in Etabs. Okay, so if it is a 3-story building, 3 into 3, 9 degree of freedom minimum you require the Etabs to calculate. And by default the software is calculating 12 modes of vibration. Okay, so you need to just check if it is okay, then you did no need to change. But if it is more than 12, then you have to manually enter how many modes of vibration I have to calculate in Etabs. Okay, so here you can see mode 1, mode 2, and mode 3. So mode 1 is in the lateral direction where all the displacements are positive. Okay, so displacement vector is phi and it is all positive, then it is a mode 1. Mode 2 means one positive and others are negative. So it is changing sign only once. So that is second mode of vibration. Third mode of vibration, you can see here it is positive, negative, and then again positive. So it is changing its sign 3 times: positive, negative, positive. Here it is negative and positive. Here it is only positive. So this is where you can identify when you will solve the matrix, you will get answer. From that, you need to identify what is the first mode, what is the second mode, what is the third mode. So if it is a fourth mode, then it will be positive, negative, positive, and again negative. So you just need to check the signs, how many signs change it is taking place. If it is changing 4 times, then it is 4 mode. If it is 5 times, it is 5 mode. So that is how we identify the modes of vibration. And we will see in the code also how the response spectrum analysis should be done and how many modes shall be uh, present in your system, that 90% mass participation should take place. So suppose the mass is M1, M2, M3 and 90% mass of the total building should participate in the vibration. So what you will do, you will calculate the mass participation for first 3 modes, mode 1, mode 2, mode 3. If the mass calculation is not equal to 90% of the total mass of your building, then that analysis needs to be redone and your building needs to be replanned. So 90% mass participation has to be there, and your 65% this mode in each particular mode, okay, your 65% mass should participate. Let's say in first mode the mass participation is only 30%, then that building is rejected. So in each mode your participation of the mass should be at least 65%. Okay, so that is also we will see in Etabs. So but just right now you remember. Okay, so this is the diagram, basic diagrams in dynamics that we use, and if we have to do it manually then we do it like this. So now if we are doing a forced vibration, free vibration, that means your term on the right hand side is 0. Right now on the right hand side it is ft. So ft means it is a forced vibration, free vibration means it is 0. So forced vibration, what force is acting on your system, whether it is a time history analysis or whatever the force is acting, you will apply it on the right hand side and then you will try to solve the equation. When you will be able to solve the equation, then you will get what internal forces are generated. So there are external forces and we need to calculate the internal forces in the system. So right hand side is what? External force. Left hand side is internal force in the system. So internal forces are dependent upon what is the mass, what is the damping, and what is the stiffness of the system. So it is depending upon our building. Okay, so it is the inherent property of the system. So internal resistance should be equal to the external resistance, then only equilibrium will take place. So that is the basic equation. This is called equation of motion. So whatever the motion of the building is taking place, okay, so it should be able to and due to the motion how much forces are generated, the internal resistance should be equal to that. And it is vice versa, whatever the internal resistance is generated in the system will be equal to the external force. So that is why we calculate internal resistance on the left hand side and we say that it is equal to the external force. Or you already have a force with you, then you will try to equate with it, and your stiffness and damping and mass matrix needs to be made in such a way that it is in equilibrium with the external forces. So that is part of your building planning before design. Okay, so design will take place after that. Okay, so let's see a solved example in which we have a mass. Okay, mass at the top story is 1, it is 1.5 and it is 2, and every time the mass has to be in kg unit. You have to remember the mass should be in kg and stiffness should be in kilonewton per meter. So unit of stiffness is kilonewton per meter and unit of mass is kg. Then only you can manually do the analysis. So that is one point you should remember, that mass should be in kg. So here you can see it is a 3-story building. So they have created a fixed support here, that is base of the building. They have given mass m1, that is the top story. I do it reverse. I take at ground story as the mass m1. Here it will mass m2 and mass m3. This will be k1, k2, k3. So all columns have the stiffness. Vertical elements have stiffness. Currently the vertical elements are only column. If shear wall and infill are there, their stiffness also will be calculated and this diagram will be created. And from this we will create a diagram like this. So that is a mass m1, m2, m3, k1, k2, k3. So how many stories are there? That much mass and that much stiffness will be there in your building. So this is the matrix that is created. Okay, mass m1 and m2 and m3. So all are diagonal. So if there are 100 masses, 100 masses will only be in diagonal. So mass matrix is always a square matrix. So square matrix means how many rows are there, same number of columns will be there. So if there are 100 masses, it will be 100 by 100 matrix. Okay, same rows, same number of columns. So right now 3 masses are there. So m1, m2 and m3. And x1 double dot, so mass into acceleration is the equation. So x1 double dot, x2 double dot, x3 double dot plus stiffness matrix. Okay, so here you can see it is k2 plus k3. So either you can take it as k1 plus k2 or you can take it as k2 plus k3. So either you take from the top or from the bottom. Okay, so if it is from the bottom, then it will be k1 plus k2, and if you are taking from top, then it will be K2 plus K3. Okay, so whatever the stiffness is on the top, okay, that should not be added with any other story. So on top it is K1. Here it will be negative K1 minus K1. So it is a given format. Okay, and it is K1 plus K2. So as you will go below, the stiffness will be added. So first it is K1, only stiffness K1. Then it will be K1 plus K2 here. Then at the ground level, it will be K2 plus K3. So any if you are going means below the top story level, so the considered story plus the above story stiffness needs to be added. So if it is story 2, then it is K2 plus K1. If it is ground story, then it is K3 plus K2. Okay, so that is how it goes. So K1 at top, K2 plus K1 on story 2, and K2 plus K3 on ground story. Rest, it is minus K2 minus K2 minus K1 minus K1. So it will remain the same. So it's depending upon your problem, this will keep on changing. Okay, so if you refer the textbook more, solve the problems more, you will come to know that how this matrix is generated. And this is x1 x2 x3, that is the displacement. Okay, so mx double dot plus kx is equal to 0. So why they have done 0? Because this is eigenvalue solution, and eigenvalue solution is for the fundamental mode only, and that is a fundamental mode means free vibration. So in free vibration on right hand side it has to be 0. So we are estimating the basic property of the system that we are designing. We are not right now concerned about how much force is acting on the system. We are concerned about what is the building we have defined and created, and what is the basic behavior, inherent basic behavior of the buildings. That's why external force is 0. Whatever the fundamental internal resistance is generated, that we want to calculate. Okay, that's why it is equal to 0. So for behavioral analysis, we keep it either as 0. So this is part of behavioral assessment of the building. Now replace all terms. Okay, you will get mass matrix and stiffness matrix. This will be stiffness minus omega n square into m equal to 0. What is omega square into n? It is the natural frequency of your building. So your time period is dependent upon natural frequency. So what your time period is 2 pi by omega. Okay, right now it is omega square. So if you want to calculate the time period, it will be 2 pi by omega. So once you calculate omega, then only you can calculate the time period. So this equation is called eigenvalue solution, in which stiffness matrix is there, minus omega n square, that is also a matrix, and mass matrix is there, which is equal to 0. Okay, which remains constant every time. So this here you can see stiffness matrix minus omega n square mass matrix is equal to 0. So now here you can see omega n square by 600 is equal to lambda. We solve the equation, then we get radian per second is the frequency. So omega 1 14.5, omega 2 31.1, and omega 3 46.1 radian per second. So radian per second is the unit of omega, which is called the natural frequency of the system. Okay, so natural frequency is there. Now from natural frequency 2 pi by omega, you get the time period. So in mode 1, the time period will be 2 pi by 14.5. Mode 2 time period will be 2 pi by 31.1, and mode 3 time period will be 2 pi by 46.1. Okay, so T1, T2, T3. For 3 modes, okay, there are 3 masses, so 3 modes. For 3 modes, you have got the time period of the building, and the time period of all 3 modes should be separated by 10%. So if T1 is, let's say, 1 second, then T2 has to be 10% separated. Either it can be 1.1 or it can be 0.9. So it can be less than 0.9, or it can be more or equal to 1.1. It cannot, both cannot have the same time period, and the difference has to be at least 10%. So if the time period T1 is 1, then time period T2 cannot be 0.9, less than 0.9, it cannot be less than 0.9, and it cannot be less than 1.1 second. Okay, so that is what we need to ensure. And similarly for T3, when we see T1, T2, T3, all time period, the 10% difference should be there. That is what we need to ensure. So that is what is the basic planning of the mass and stiffness you need to do in your building so that this criteria can be satisfied. Okay. Okay, so that is right now, that is the particular thing I just wanted to cover with regard to dynamics. Okay, so these are the mode shapes that we are interested in. If time permits, we will do it in MATLAB. Okay, so this is basic manual analysis. So if it is clear to you, then I can continue forward in Etabs. Okay, Jan is clear. So if you are clear, then I can move forward. You just give a thumbs up, then it is okay for me. So Subhash, is it clear? It is basic.
Yes, sir. Yes, sir. Sir, you said for modal participation factor for X direction, it should satisfy 65 percentage.
Yeah.
Yeah, sir. Is there any class in Indian standard codes regarding this one?
Yeah, we will look into we will look it into the code also. So what they are
Okay.
saying that if it is not 65%, that means it is a mixed mode. So when it is a mixed mode, then modal coupling may take place. So the difference in the time period. Okay, so if it is 1 second, 10% difference should be there. So that modal coupling do not take place. So mode 1, mode 2 should not occur at the same time. Okay, so if a x direction the building is going, and similarly at the same time in y direction also the building is moving. So it will be like in both directions x and y, the building will start moving if the time period is nearby in both the directions. Okay, so there are x direction, y direction, and torsion. Three directions are there. Now, if the building starts moving in two directions at a time, then it is called modal coupling. Or it is moving in x direction as well as twisting, then that is also a modal coupling. So modal coupling should not take place. That's why we are keeping the time period difference of 10% in each mode, as well as the significance of the 65% participation is that in the life of the building, okay, in its entire life, when we are doing the free vibration analysis. Okay, free vibration analysis means whatever is the fundamental property of the system, that is what we are seeing. Okay, so in free vibration analysis we are calculating all modes. If there are 100 modes, we will be calculating for 100 modes, but in the life of the building only 5 modes will occur, that is estimated. Okay, so that is why they are telling that first 3 modes of the building, let's say it is a 60-story building, then a 60-story building, the first 3 modes, mode 1, mode 2, mode 3. Okay, mode 1, mode 2, mode 3, you calculate the mass in each of the modes. Okay, 65% should be there. Otherwise, what will happen? The higher modes will govern in free vibration analysis that you are doing. But in reality, higher modes will never be created in your system. So up to 5 modes only the building will be excited, and remaining modes of the, there's a 95% 95 modes will not be excited. So that is the reason they are saying the mass should be higher in the lower modes, so that when building is excited in the first 5 modes, the actual mass should participate so that resistance will be generated. If mass is not participating, then the resistance will not be generated in your system. Okay, so even if you have 100 modes in free vibration analysis, in reality it is a forced vibration. Okay, so whatever equal to 0 we have done currently to solve the 100 modes, that is not a reality, just the behavioral assessment of the building. In reality, there will be only 5 modes on your building. So all that's why first 3 modes are given importance in all codes around the world. Okay, first 3 modes are very important. They generate the resistance in the structure. So modal coupling should not take place. That is taken care of by the time period, and your internal resistance should be generated in the structure. That's why first 3 mode mass participation has to be higher. Okay, I hope it is clear why it is done. Modal coupling should not take place, and the excitation range of in the reality, it is the first three modes that will be excited in its lifetime, and the resistance should be higher in the lower modes. That is the main reason for that. Okay. Alec, is it clear?
Clear, sir.
Okay. Okay, so we can move forward. Same we have when we see this building. Okay, I hope my Etabs model is visible to you. Let me share again. Okay, so my Etabs model is visible to you, and now I show you again what we were seeing in that particular example, that at each floor we have a mass. So right now there are 7 masses. Right now there are only columns, so we will calculate how many columns are there in our building. So for that we have 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Okay, so there are 5 by 5 grids are there. So we consider 25 columns at each floor. Okay, so there are 25 columns at each floor, and we need to consider stiffness of 25 columns so that we get a K1 for ground story, similarly K2 for second story, third story, fourth story, fifth, and sixth, seventh story. So there will be 7 stiffness matrix created if we do it manually. And the stiffness of the column is taken as 12 EI upon H cube. Okay, E is the your modulus of elasticity, I is the moment of inertia. So 12 times EI of the column divided by height the whole cube. Okay, so for each column we need to do this. So 12 EI by H cube for 25 columns per story we need to calculate. So at first 3 floors the column size is 750 by 400 mm, and above it is 700 by 450 mm. So in which direction you are considering, that is important. So let's see again into the section properties. I hope you know how to calculate the moment of inertia I. So moment of inertia I is already available in your table here. Okay, either it otherwise it is BD cube by 12 for the column. So in which direction you are considering, either it is BD cube by 12 or it is DB cube by 12. So that you need to consider for manual analysis separately, because software will do it by itself. But in Excel you need to do it uh, uh, be careful about that. So this column is 750 by 400 mm. So if I considering the moment about the axis 3, okay, if it is the moment about axis 3 is there, then your B will be 400 mm, your D will be 750 mm. Okay, so if the moment is about the 2 axis, okay, if moment is about 2 axis, then it will be what? Your B will be 750 mm and your D will be 400 mm. So it is BD cube by 12 or your DB cube by 12. So you need to just consider the particular direction when you are doing manual calculation. Okay, so that is I value, and stiffness will be same, 12 times EI by H cube. So your K value K1 will be 25 into 12 EI by H cube. So right now all columns are of the same size. Similarly, if they are of the different size, then 12 EI by H cube of different has to be done. Just hold on a second. Okay, fine. Okay, so moving forward, this was what we had defined, created our model. We have given all properties. We have given the rigid diaphragm, and rigid diaphragm, that means we are doing the lump mass modeling. Lump mass modeling, that means your mass at the story level is rigid, that means slab and beams stiffness is equal to infinity. Okay, so what will happen, your stiffness is infinity, that means they will have zero rotation, or they will not be bending. So when it is not bending, it will not take part in the deformation of your system. Only part remains is the stiffness will be given by only columns. So if it is a rigid diaphragm, then only columns are the participating in stiffness. Otherwise, if it is a semi-rigid diaphragm, then beams also should participate in the stiffness, and hence your matrix becomes complicated and it is not solvable manually. Okay, so for rigid diaphragm, we can solve it manually. That is what I had showed manual how they do. And we need to create an Excel for, so right now I would be doing this analysis in Etabs. You need to do it in Excel. Okay, so if you do it in Excel, it is good for you. MATLAB also it is possible. If you don't know MATLAB right now, Excel also can do this. Okay, so for 7-story building, it is possible to do it in Excel. Okay, so we had defined the material properties last time. We had done the section properties. Diaphragm we have defined. We have defined the response spectrum function. Okay, so that is a zone 4, 0.24, response reduction factor is 5, and this is design basis response spectrum, DBE, not MCE response spectrum. So in the Etabs 2019, it is a design basis earthquake response spectrum. And I will just delete the time history that we had defined last time, so that our analysis is not hindered. Now, very important thing, to calculate the mass in the software. If you are doing it manually, you will calculate the mass by yourself, but in software you need to give the mass source. So from where to calculate the mass, the software should know. Okay, so you just modify it. Right now we have not created any load patterns. So first we will create the load pattern so that we can do a mass source definition so that the mass is calculated. So load patterns, okay, we go to load patterns. In that, all type of loads need to be defined. So right now dead load, live load is already defined in Etabs already, always it is there. Let's take earthquake in X direction. Take seismic. Okay, seismic and seismic drift are there. Drift is not suitable for our case. As per the IS code or as per the Euro code, we don't take drift. But if your building is flexible, and only thing is your overall drift of the building is limited in seismic parameter, it will be as per your code. If you give drift, then it has no limit, so it will not follow the code. It will take maximum limit, that is your building is going to take. Here it is restricted by your code, so that's why we take as the seismic load type. Here it is 2016, and add new load, modify the load. Okay, so eccentricity has to be 0 right now, because we are doing the static analysis. In static analysis we will not take any eccentricity. Okay, but if your response spectrum you are not doing, if you are not doing the response spectrum, then you need to take eccentricity. If you are doing response spectrum analysis, that is the dynamic analysis, then it is not required. Is it clear? So for, let's say, building of 3-story, for building of 3-story, response spectrum is not required. So I will take the eccentricity, because I will not be defining the response spectrum. But if you are going more than 3-story building, where response spectrum is not required, then more than 3-story where response spectrum is required, then I will take either X or either Y. Right now I am taking the X direction earthquake force. Okay, and response reduction factor is 5 for spatial moment resisting frame, and it is 0.24 as per our code. Zone 4 we are taking for India. Similarly, for different codes, the different zone factor need to be taken. Importance factor 1 is taken. Now important thing is you need to assign what time period has to be taken. Okay, so this approximate time period, will be equal to the time period of the bare frame. If you take American code, Euro code, or any code, okay, if you are selecting this option, then it is the time period of bare frame. So in your code, time period for bare frame will be given, in which infills are not there. Okay, so you will take this time period directly. It will take automatically. Right now it is 0.075 h raised to 0.75. So that will be calculated by the software. So as per the IS code, it is 0.075 h raised to 0.75. H from software, it will calculate. CT value is 0.075. So for bare frame, you take approximate. Program calculated, that means it will take from the response spectrum method. So if you are doing response spectrum method, in which the dynamic analysis is done, which may be accurate, may not be accurate, because in dynamic analysis we are not considering the infills generally. So and many other things. So stiffness of many portions of the building are not considered in our matrix when we are solving the matrix or generating the matrix. We are neglecting that. So that is why the time period may be less. Okay, so that is when we generally take a user defined time period. So user defined time period is the time period in which the infills are considered. Okay, so infill of the building are considered. Here it is a bare frame. If no infills are there, then we take approximate. If infills are there, then we take the user defined time period, and we calculate the time period as per our code. Okay, so as per the IS code, it is 0.09 into height of building divided by square root of the base dimension. Okay, so uh, just yes, I can type it here. So no need to do any Excel or open anything calculator. 0.09, okay, is my factor. Multiply by height of the building is 21.2 divided by square root of the base dimension. So base dimension, when we are saying, so if it is in X, then X direction, the base dimension is 24. Okay, that we had seen. In Y direction, it is 20. So when we are calculating force in X direction, it is 0.09 h upon square root of 24 meters. So base dimension is 24 meters. So once we do that, okay, so time period is calculated. We will take only the first three digits. Okay, it is 0.389 second. Okay, so it will be around 0.4 second, or it is 0.389 second. That means our building is acceleration sensitive if we are taking it as infill. Okay, so infill we have considered, but we are not modeling the infill in the building. That's why when you do the program calculated option, the time period will be different. It will be same as the base bare frame time period. Okay, so it will be nearby that. So that is why we are whatever your condition is there, it is very important to calculate the time period based on the formula. So for bare frame approximate, if you are sure that your program calculated time period is accurate than the code time period, which is based on the real buildings, they tested the real buildings, real stiffness, real mass, real elements in the building, and they have given the formula. So minimum we have to follow the code. So code has a formula given to us based on the this uh, testing on the constructed buildings. Okay, so existing on ground buildings, they tested and generated a formula. So if we are sure that our mathematical model, so our software is a mathematical model we have created, on paper also mathematical model is created. If you think that it is 100% same as the building, which is a very rare case, then you can go for program calculated. Otherwise you have to keep for these two cases either approximate or user defined. Approximate means time period for bare frame, user defined means time period for infilled frame. Okay, so if that is clear, we will move forward. So it is 0.389, 0.09 into h upon root of base dimension. So that is created in x direction. Similarly, we will create in y direction. Okay, everything remains the same. Add new load, modify. So instead of X, I will take Y option. It is 0.24 and it is response reduction factor is 5. User defined, again, it is 0.09 into 21.2 divided by SQRT of square root of the base dimension in Y direction is 20 meters. Okay, so this is the formula for that, 0.09 edge upon root of D in Y direction. So I will only take the first three these figures, that is 0.426. Okay, so that is 0.38 something, and this is 0.426. So in both directions we have the time period. So flexible in Y direction. So building is more flexible in Y direction because time period is higher in Y direction. So higher the time period, that means in that particular direction the building is more flexible, right? Okay. Just a minute. Somebody is waiting.
Excuse me, sir.
Yeah.
If we have shear wall on the lower part of the basement, sir, we have to take the height from above the basement, sir. In that, if we that modify that EQX, sir, one time, sir.
Just a minute. Hold on. Huh? Okay. Yeah, you were talking about basement, right? If we take from the basement, from below the basement, if the time period is taken, then height will be different. That is what you are saying, right?
Yes, sir.
Yeah, so that option we will see. Right now we have kept it simple. So basically on ground the building is there. We have not considered the basement. Once we add the basement, then our conditions will change. The time period, the height below the basement also will be considering. So your total height will be from top of the foundation. So always we consider from top of the foundation to the roof level, the height of the building. So when it is a basement, then from top of the foundation to the top of the roof, that much height we need to consider. So there are various categories that we will also see when we open the IS 1893 or any other code. So that is same, it is followed. So we'll see when we open the code. Okay, for today, the building is very simple, and you take it, you assume that this is top of the foundation. Okay, so that is what we have considered right now. So this is the either the plinth level or it is top of foundation right now that we have considered in our building. Okay, so that is what happens that that is if I see the elevation of the building, right? So now this is the ground floor. You know that columns go below the ground up to the top of the footing. So always you should remember that whatever height you are considering the building, the height should be from top of the footing to the roof level, not just from the ground level. Clear? So that is very important. So in what cases, what we will do for a particular time period, that we will also consider separately. For this condition, it is taking from the base level up to the story 7, that is 21.2 meter. That is the height of our building. So that is how we defined in load pattern earthquake X and earthquake Y. Okay, so right now we are considering the super dead load. So in super dead load, that means I will consider the floor finish right now. The floor finish that is under super dead load, I will add that load. Okay. Another is the infills. The load of infills I need to calculate and apply on the perimeter of the beams. Okay, so that is also super dead load. So whatever is the permanent load is there, either it is a dead load or a super dead load in Etabs. Okay. So there is a live load, dead load, super dead load, and seismic load. So that much definition we have done right now. If there is a wind, then separately you need to specify a wind load case. Okay, so Basically, the building should be designed for earthquake plus other loads, that is the dead load, live load, wind load, all loads. If it is in the snowy area, then snow load will also come. So all those loads need to be defined in the load patterns. So that is the thing we have done right now. We are doing response spectrum analysis. So eccentricity 0 we have considered. Now we can go to the mass source. Okay, in mass source, we will tell which mass to consider. So specified load pattern. So whatever load pattern we have specified, from that we'll tell take the dead load, take the floor finish load, then take the infill load. So all that are part of the dead load, and our live load is up to 3 kilonewton per meter square. So when live load is up to 3 kilonewton per meter square, your live load factor will be 0.25. So dead load plus 0.25 times the live load we have considered. Here, when we consider the vertical earthquake, right now we are not considering the vertical earthquake. If you are considering vertical earthquake, then you have to take on this option. Right now, we are not considering the vertical earthquake. We are considering the earthquake only in the lateral direction, either in X direction or in the Y direction. Okay, so that is why this option is not required. So this is the mass source we have given. So from this, the software will calculate the mass and form the mass matrix. This P delta option, it should be specified always, whether you are doing a 1-story building or a 2-story building, any building you are doing, it should be specified here. Okay, preset P delta option. Now the revision of IS 16700 has opened the door that we can use a preset delta option. Okay, amendment has come in 16700. So now it is official. Previously it was not official in the code, officially mentioned in the code. Now it is officially mentioned. So what we will do, 1.2 times the dead load. So whatever are the dead load, 1.2 times. Okay, and whatever are the live load, it is 0.5 times. That is, we add it. Clear? So this is preset pre-delta option. Now officially, as per the amendment of 16700, we can follow. And this is what I was previously following. But some people have problem with this application. They say that it may not be correct, but now the code has also approved this. Okay, so we for p delta analysis, we are using preset p delta option. Okay. Okay, so now load cases are there, load combinations are there. So we see the load cases, then dead load, live load, modal analysis. So this modal analysis, you need to be very careful. Okay, modify or show. It is a eigenvalue solution right now you are doing. Okay, so whatever we had seen in the textbook, same eigenvalue solution, you are choosing it here. Okay, so preset p delta option should always be on in this case. Now here maximum number of modes. So 7 3 ja 21. So 3 per story should be there. So 7 3 ja 21 have to be there minimum. So I will give it 25, let's say. Okay, so calculation will be done for 21 because I have given it a rigid diaphragm and it is a lump mass model. So for lump mass model, per story 3 has to be given. So 7 3 are 21. Now it is 25 I have given. So now all modes will be calculated for my building. Okay, very important part in this, you need to remember that. It is a modal analysis, eigen, p delta preset is given, and for how many modes you require, that you need to enter. Okay, 3 per story. So that we have given. Earthquake in X is already there, Y is there, floor finish. So whatever the patterns you defined, they are all created here. Okay. Now what we need to give, we need to add a new load case here. Why we are doing response spectrum? So for response spectrum load case, we need to give eccentricity. Okay, that we will see later on what eccentricity is there. So I had told you that there is center of mass and there is center of rigidity. So if they are not coinciding at your each floor, okay, it is a calculation for each floor. If you do it manually, it will take you a lot of time. Okay, So when you will create an Excel, you will see that you will take around 1 week to create a whole Excel for response spectrum method. So software is doing automatically. So first we will see what is happening. Okay, then we will define the response spectrum case. So we have defined all load cases. Okay, right now I just want to do analysis. That's why I'm not defining load combinations. Otherwise, for your design, concrete frame design or shear wall design or slab design, we need to tick all three if all three are there. When we are giving it as a rigid diaphragm, and this when we are giving it as a membrane. Okay, so when you are defining your slab as a membrane, then software cannot design your slab. If it is a shell only, then concrete slab will be designed in Etabs. So while you are defining your slab in the define section, you when you are selecting as membrane, this option you should not tick. Okay, and you can use this option to convert the user defined combinations. That means after definition you will be able to edit it. If you are not selecting it, you will not be able to edit that particular load case. So I generally keep it open and I try to edit it. Okay, so this we will do when we are going to design it. Right now we are going into only analysis part. So in analysis, what we will do it here, we will go to analyze. Okay, you can see what load cases should be run and should not be run. So if you have some load case that you don't want to run, so I don't want to run, let's say earthquake X. So I will select this run or do not run. So it will do not run this earthquake X analysis. Okay, but I want to run it. So either run or do not run, you can select whatever analysis you want to run or do not run. But here we have not defined the floor finish yet. So we'll give the floor finish as well as the infill load on our building. Then only we can move forward. So this is the option in which if you want to see your bare model, this option you can select, or either you can do F4. Okay, so I am selecting this. So my model will be means without any undeformed shape. So show undeformed shape, your model is ready. So now again floor finish on the roof and floor finish on the floors below it. So on the roof you are considering 1 kilonewton per meter square for the tiles that you will be providing. Your tiling flooring that you will be doing, that is 1, plus waterproofing. So on roof the floor finish will be of 2 kilonewton per meter square roundabout, and below the floors below the roof it will be 1 kilonewton per meter square. So that way we will select first, select the object type, we will select all floors. Okay, so I have selected all floors, but I want to select only the roof. So I will go select deselect option. In deselect option I will select the stories that I want to deselect. I will deselect all the stories below 7 story. So I have deselected it, close. So my selection is only 7 story. Now I will what do assign. Again you are applying load on the slab, that is a shell element. You go to shell. Okay, here once when you see it here, apply load will not be there. Here you have to go to options of this part, below part. So same options are repeated here with the name load. So here it is joint, it is joint load, frame, then is frame load, shell, then shell load, tendon and tendon load. So when you want to apply the load, then you have to go to shell load and apply it as uniform. Okay, it is a uniform load. Okay, so I go to uniform load, and this is a floor finish, and it will be 2 kilonewton per meter square on the roof. Okay, so here you can see that 2 kilonewton per meter square is applied on the roof. Now I will again select object type, then it is again floors, then I will go to deselect and object type, the story. I will only deselect the 7 story because I have already applied load on that. I want to apply load on the below story. Again, I go to the shell loads, uniform, Floor finish, it is 1 kilonewton per meter square. Okay, so if you want to check it, you can go to plan. Here you can see on 7th story it is 2 kilonewton per meter square. Below that there is 1 kilonewton per meter square. So you can confirm that whatever you have provided is correct. So once that is done, now what I will do, I will select the beams. Object type, beams, select. Now my infills are not on the roof. Okay, so on roofs I cannot provide the load of the infills. So I want to deselect the beams on my 7th story. So I deselected. So all beams are selected and I will provide the load of the infill. Now how to calculate load of the infill? I have considered AAC block. So AAC block, the thickness is 200 mm. Okay, the density is 6 kilonewton per meter cube. Okay, so density into your area. Okay, density into area. So area will be what? Thickness into height. That we will apply on the beam as a UDL load. So 0.2 into 3. It will be how much? 0.6. Okay, 0.6 into 6. It will be 3.6 kilonewton per meter. So 6 kilonewton per meter cube is the density, which is multiplied by the thickness 0.2 multiplied by 3 meter height. Okay, so 3 into 0.2 will be 0.6 and 0.6 multiplied by 6 will be 3.6 kilonewton per meter. So I will go to assign, then I will go to now frame load. Now if it is a beam and column, then it is frame element. If it is a shear wall and a slab, then it is a shell element. Now it is a frame element and I am applying a distributed load UDL. Okay, and that will be part of what? Infill. So that I will provide as 3.6 kilonewton per meter. Okay, so now on the top of the building I will be providing a parapet. Okay, so for that again I will go to select. I will select the object type, beams, select. Then I will deselect as per the story. All story I have assigned. Only on top I want to apply the load of the parapet. On parapet I'm assuming as 1 meter. So height is 1 meter. So it is 6 kilonewton per meter cube into 0.2. Okay, so that will be 1.2 kilonewton per meter. So I will be again going to frame load, distributed, and I will apply infill as 1.2 kilonewton per meter. Okay, so this is the infill load I have applied, floor finish I have applied. So I have completed the definition of all loads. So now I can do the analysis part. Okay, and I have given the preset P delta option. So your P delta analysis will be done. After that, you don't have to worry about P delta analysis. So preset P delta, basically P delta analysis is a non-linear analysis, but using preset P delta in linear analysis, it is already done. So your non-linear analysis of P delta, that is geometric non-linearity, is considered by preset P delta option. So you don't have to do any non-linear geometric non-linear analysis. Okay, so that I will show you later on what is the difference between that. But right now your analysis is simplified, and in your linear analysis it is P delta already included. Okay, so this was about different loading and framing options in Etabs. So those who don't know, that many don't know Etabs, that is why I'm covering it in more detail. Just hold on. Yeah, you can see UDL load is applied 3.6 and 1.2 UDL load is applied on the beams. Okay. Okay, so the load of infills we have considered, but stiffness of infills we have not yet considered. Okay, so generally for AAC blocks, they do not consider the stiffness of the infills. Okay, so your time period formula should change accordingly. So if you are using a brick infill, okay, then they consider the stiffness of the infill. So your time period formula will be 0.09 h upon root of d. But when you are doing the AAC blocks, then they say that its stiffness should not be considered. But I still consider the stiffness. That's why, however, the formula then should not be 0.09. So for brick infills only, the formula is valid currently. So if you are using AAC blocks, you have to be careful that if you are using 0.09, then it may underestimate the deformation. The force will be high, but your deformation may get underestimated. So that is a very critical aspect that you need to take care while you are defining a infill, whether it is a AC block or it is a brick. So in AAC block, what I will do, go again to the load patterns. I will go to modify. I will select approximate. That is a bare frame. So I will now consider it as a bare frame because I have defined a AAC block. Again, you save your model. So keep on saving your model. Otherwise, your work will get deleted. Okay. So now we are ready to run the analysis. So all these load are there. Very important is you should remember that calculate diaphragm center of rigidity option you need to tick. Otherwise, it will not calculate CR. If CM is and CR is not calculated, CM is automatically calculated by the software. If CR is not calculated, then you don't get eccentricity. That will see what eccentricity is that at diaphragm eccentricity. If CM and CR are not coinciding, then the distance between CM and CR is called eccentricity. Okay, so now I will run the analysis. So right now we are doing static analysis, equivalent static analysis in Etabs. Okay, that is what we are doing right now. Equivalent static analysis, not the dynamic analysis. So dynamic analysis is response spectrum method or time history analysis. So while the analysis is running, somebody can ask their question if they have some question regarding this. Very basic session today we have. So that all should be able to model their problems in Etabs. That is the agenda.
Sir, I have a question.
Yeah.
Sir, for diaphragms, can we define multiple diaphragms in one building?
Multiple diaphragms means either it should be rigid or it should be semi-rigid. Define anyone D1, D2, D3, D4, D5, D6. But if all are rigid, all should be rigid or all should be flexible. That is the only thing. And once you change the diaphragm, then what will happen that at a particular story, the location of forces will be different. Okay, so for each diaphragm that you define, the force will act only at that center. Okay, if diaphragm D1 and D2 is applied, then the force will be on D1 you will see at the center and on D2 you will see at the center. Okay, so how many diaphragms you define, that many forces will be created on your particular floor. Okay, that's why it is always better to define a particular one diaphragm. Otherwise, software also does it, calculates it, but generally it is not done different diaphragm on the same floor.
Thank you, sir.
Excuse me, sir.
Yeah.
Sir, for performing the static analysis and dynamic, for what type of structure you have to perform static and what type of structure you have to perform dynamic analysis? Whether it depends upon the height or geometry.
Yeah, as per the IS code, IS 1893-2016, any building that is more than 3-story, let's say 15-meter height, okay, and regular building I'm talking about. If it is irregular, then in all buildings you need to do response spectrum method, dynamic analysis. If it is a regular building and less than 15-meter height, then you can go for static analysis. Otherwise, you have to go for dynamic analysis. That is the criteria given by the code. So regular building up to 3-story, static method analysis to be done. Otherwise, all are response spectrum method of analysis. That is clearly mentioned in the IS 1893/2016. Okay. So now I think the analysis has run, and let's see. What we have to see is display option. In display, we go to show tables. So in tables, we will see the calculation of center of mass and center of rigidity. Okay, so where it is available in analysis results option in structure output. Okay, once we click this structure output, there will be other output items, and in that there will be center of mass and rigidity. Okay, so that is one important table that we require. Second table that we require is modal participation mass ratios. These are very much important. Okay, so modal load participation ratio, all are different, but we what we want to check is modal participation mass ratios that are very much important. Okay, so that too we will see right now. So now you know that this table can be exported to Excel directly. Okay, so if I select this export current table to Excel, so you can export this table to Excel and calculate the distance between center of mass and center of rigidity. Right now you can see in X direction, X center of mass, okay, and X center of rigidity. Both are same value. So your static eccentricity is 0. Okay, so we will further go into that in next session. What is static eccentricity? What is dynamic eccentricity? That we will see. So your static eccentricity is 0 because CM and CR both are coinciding with each other. So 12 minus 12 is 0. Similarly, in Y direction, it is 0. So right now our building is symmetric. That's why CM and CR, the distance is 0, which is a good option for us, because if the eccentricity is there, torsion force will be created. So if torsion force is created, then you need to you require higher reinforcement for that. Okay, so right now the torsion will be only 5% that we consider. So in your plant dimension 0.05 of B. So B means when you are calculating the X direction force, then B will be the dimension in Y direction. If you are calculating force in Y direction, your B will be the base in the X direction. So that is how you need to consider that base. Okay, so right now it is 0 0, static eccentricity is 0. So your calculation of eccentricity is 1.5 ESI, that is eccentricity static, which is ESI 0. So 1.5 into 0 plus 0.05 of the B. So for X direction it is 24, for X direction it is 20, and for Y direction it is 24. So base dimension that you need to choose in the proper way, that in X direction the base is 20 and in Y direction the base to be considered is 24. Okay, so that is critical. In X you take B of Y and in Y you take B of X. Okay, so that will 0.0 of B. So now what I will do, unlock this model as I came to know of eccentricity. Okay, I will again go to the define section. I will go to load cases. I will add a new case. Okay, now positive eccentricity and negative eccentricity two are created. I will also share that in the next section, but right now we are creating it RSM X, that is positive eccentricity, linear static. Right now load case is linear static. You need to make it response spectrum because that is what you are doing. Add acceleration. You need to add acceleration here. You need to just check U1 means X direction, U2 means Y direction. Okay, and U3 means vertical direction, and R1 means rotation about X, rotation about Y, rotation about Z. Okay, so right now we are taking the earthquake in X direction. Your response spectrum is what you had defined, Z4, that you need to select. Other should not be selected. What is your particular response spectrum that you need to select? And your scale factor is 9806.65. In Etabs 2019, your scale factor is right now 9806.65. Okay, it is a model case, it is CQC method, and you need to take when it is only 5%. Okay, you just need to mention it 0.05 here. You don't have to do anything else. Otherwise, what you have to do for each of the story level, okay, so for each story I will have to enter. If it is not 5%, then I will have to enter for all stories. So calculate for each story what is CM minus CR. For story 7, CM minus CR. For story 6, CM minus CR. Right now it is all 0. Okay, so that is why it is not required. So currently your eccentricity in static direction is 0, and in that you have to add 0.05 of BI. So your whatever you are taking here, it will be calculated here. You can enter it manually, but right now we have a direct option for 5% eccentricity as 0.05. So it will calculate automatically for 0.05%. Otherwise you calculate and then enter it here as per your formula. Okay, so that is in positive direction. Okay, second new case that we consider, that is RSMX in negative direction. So that also we will see through a diagram what is positive, what is negative. This is again in X direction, so it is U1, it is CQC, SRSS. Here we just have to give minus 0.05. So negative means minus 0.05. It is only 5% eccentricity. Okay, add new case. Then RSM in Y direction with positive eccentricity. It is a response spectrum. Add U2 will be there. Here it is Z4, that we should not miss. The positive eccentricity is 0.05 in Y direction. Here we had not done this, so in X negative. Okay, so your option here, add copy of the case. So I have added copy of the case, so I can make it negative, RSMY negative. It is U2 Z4 and it is minus 0.05. So RSMX positive, RSMX negative, RSMY positive, RSMY negative. So all 4 response spectrum load cases you need to create for you. Okay, so that is important. So if it is a vertical earthquake, again you need to define it that way, because in vertical earthquake this U3 direction will also come. Okay, so for response spectrum that in U3 direction, what you will do, just a minute. So let's see when we'll see the vertical earthquake. Right now it is a X and Y direction. So X created, Y created. So vertical earthquake also X and Y will be created, but in the Z direction, the 0.3 factor will be added. That we'll see later. Okay, so that is, these all load cases you need to create for your building. Minimum for earthquake analysis. For wind, response spectrum is not required. That is a basic load case you can create, and the software will run the analysis. Okay, so that is done. Okay, so now we can, when we run this analysis, this is the option, either take F5 or you just click it here. And if you want to go and see again, center of rigidity should be selected, and what you don't want, you can run or do not run. You have the option. So run now, all cases to be run. So this is what we have done. Static analysis previously. From that we got the distance between CM and CR. Once we got distance between CM and CR, we took it into Excel. In Excel we did 1.5 times ESI CM minus CR plus 0.05 of BI. So as it is only 5% we have available, so we have given a response spectrum load cases with positive and negative 5%. So this is what we have done. So if anybody has a doubt, just you can ask me. Till the analysis runs. So Jan, is it clear to you what we are doing?
Yes, sir. Yes, sir.
Okay. And Binur? Binur is there? Yeah.
Yes, sir.
Yeah. So we are doing today only the basic, so that if somebody has not done the analysis in Etabs, they should be able to do it. So and it is a refresher that what all are the particular options. Alec, you have a doubt? You have raised the hand.
No, sir, till now.
Okay, okay, fine.
So if you kindly check the chat, actually I can't use the mic here.
Yeah, just the option. Okay. So what is the mass eccentricity in mass source? Okay, that we will cover when we do manual analysis, because right now we will not be able to do it. So what is happening that when there is a change in center of mass and center of rigidity, we are using a formula 1.5 times ESI plus 0.05 of BI. So software has calculated center of mass, software has calculated center of rigidity, but we have a different formula for calculating eccentricity. So whatever eccentricity is calculated by software, our eccentricity is always different as per the formula. So if what is happening, the center of mass is shifting, so that our calculated eccentricity should uh, be equal to the distance between CM and CR. So current CM and CR of the software eccentricity is different. So we try to make it the same. So we shift the CM so that whatever the eccentricity we have calculated, it should be same in the software. So that is what it is asking about. So shift your CM so that CM and CR distance becomes equal to your formula. So that is what you can do. So that is option one. Either use the shifting of the center of mass, or you give eccentricity. So if you are giving eccentricity, then you should not use the shifting of the mass aspect. So either use shifting of the mass or you do eccentricity, and calculating eccentricity is better, because as per the code, it is required to submit the calculations as per eccentricity. So if it is not explicit, then it will create a problem for the this passing of the building. So hence we should use the eccentricity part more rather than the shifting the center of mass. But two options are given by software with us. Okay. Okay, so I think analysis has run. Now what we will do, we will go to the display option again. We'll see the tables. Okay, and okay. So now your center of mass, center of rigidity is all the same. It will never change. Okay, so it is 12 minus 12, 0, 10 minus 10, 0. So static eccentricity is 0. So 1.5 into 0 plus 0.05 of width of in the particular direction. So that is done. And what we are interested in, there are see here 12 modes are created here. So we had done 7 into 3, 21 modes. Now calculation is of the 12 modes right now. So that is how much the software has calculated it. In first mode, the time period is 1 second. So in first mode means in the which direction it is. So it is in Y direction. So based on the mass, you can come to know which direction is excited first. So time period is 1 second in Y direction. And mass participation is 83%. 0.83 means it is 83%. Okay. And Rx, that is the torsion. torsion mass is 17%. So your 83% mass is in translation, and rotation it is 17%. Okay, so that is correct. Now it is more than 65%, so that is okay. Now in the second mode, you can see x direction is excited, 79% of the mass is excited in x direction. Your time period is 0.875. As I told, it should be, if it is 1, then in x direction it should be 10% different. Either it can be 1.1 or more than 1.1 or less than 0.9. Currently it is less than 0.9, so it is correct. We have our building planning is correct. Otherwise we need to change the stiffness of elements in the building, or if that is not possible, then change the plan of your building. So it is all based on either the stiffness or your plan. So try with stiffness first if it is okay. Otherwise with stiffness you are not able to modify this, then you need to change your plan in both directions. So generally square buildings will not be preferred now. So you cannot make a square building. So if you are making a square building, you have to be assured that in both direction, x direction and y direction, the stiffness should be such that the time period calculation should be 10% different. If it is not happening, you need to do it iterations. Okay, so 0.875 in x direction and 79% mass is excited. Torsion is 21% mass is torsion. So 100% mass, 79 plus 21, so that is 100%. So we can come to know in ry direction the mass is excited 21% and 79% more than 65, that is okay. Now that is the third mode. So third mode is 0.835. Okay, so 0.835 and 0.875, you can see that the time period is nearby. So when that building is excited in x direction, correspondingly it is excited in torsion. So y direction, x direction and torsion. So first three modes should be first two modes should be translation. So that means first two modes are translation. That means their time period should be higher than the third mode. Okay, so third mode time period is 0.835. If it is higher than the above two time period, then torsion will become the governing factor, which is not allowed by any code in the world. So first it is moving in x direction, then it is moving in first it is moving in y direction, then it is moving in x direction. That is called translation. Translation means x and y. Rotation means torsion. Okay, so your torsion or rotation, which is represented, that you can see that everything is 0 here. Okay, so where it is showing here, it is showing only the value is shown in rz. So your excitation is torsion. So mode 3 is torsion. So wherever this z factor is there, that is in that particular time period, the torsion is getting excited. So your third mode is torsion, which is 81%. That is also good, no problem. And your time period is 0.835. Now you should reduce this time period. Okay, so you cannot increase the time period, because if you increase the time period, then your mode 2 will be torsion, which is not allowed. So if your time period is 0.9 second, then your mode 2 will become torsion, and that is not allowed by the code. So your torsion should be in mode 3. So stiffness Gj by L. Okay, so J factor, I had told you last time that J factor is important. So you need to increase the thickness of your element so that the J value increases. Okay, and when J value increases, the stiffness of in the torsion direction increases and your time period becomes lower. So the mode will shift downwards. So if your torsion is more building is more flexible in torsion, then the mode 1 or mode 2, it can become torsion, which is not allowed by the code. So just by increasing the thickness of the elements, you are able to bring the solution as per the code. Any doubt till now in this regard? That mode 1, mode 2, mode 3. So first two should be translation, third should be, after first two, rotation can come. So that is all stiffness, related to stiffness of the element. So torsion is related to thickness. Okay, so if you increase thickness, your torsion will be shifted downwards and translation will be upwards, and that is our requirement, and 65% mass minimum should be there. Okay, so this is what we have achieved, and this is about dynamic analysis. This you need to obtain using Excel. This is the target I can give you. So read any textbook and try to solve the same problem. So I will keep this model in the group, okay, and Etabs file in the group. You can look at the Etabs file, and you can create a manual calculation based on that in Excel. Okay, so for doing the static method, you need to calculate the weight of all elements. Then if you are doing dynamic method, then you need to calculate the weight and then create the matrix and do the eigenvalue solution. And then you need to find the time period of the building, natural frequency, and the modal shape, mass participation, and your participation for the force. Okay, so that is what you need to do manually. So right now that is the sole part, a very important part that you should do in Excel. So I will just show you in in my Excel. I will just show you in my Excel. Okay, so hope my screen is clear because this is very important. Okay, so this was done as per IS 1893 2002 older version, but it does not change because eigenvalue is still the same. So analysis will not change. Either you follow a new or old building. So the problem was a 15-story building. It is located in my city, Ahmedabad. The size of the building is 30 meter in X direction and 22.5 meter in Y direction. Beams are of the size 400 by 500 mm, and slabs are 150 mm thick, and columns are 600 by 600 mm. So right now 600 by 600 columns, if you are using, then you need to make sure that the time period in the X and Y direction is differing by 10%. Masonry walls are all 115 mm thick. They are all partition walls. Okay, so now after doing the matrix analysis, okay, for as it is a 15-story building, so you can know 15 into 3, 45 modes will be there in my building for lump mass calculation. So I have considered only first three, as I told you that during the life of the structure, maximum up to 5 modes can be excited, but for 15-story building, 3 modes may be excited in its lifetime. So I have considered only first 3 modes, and I have calculated the time period in for mode 1, mode 2, mode 3 using the matrix analysis. For this building, I have calculated the modal vector. Okay, that is called the eigenvector and eigenvalues. So eigenvectors are the displacement vectors that you need to keep it here, and second is the eigenvalues, that are the time period of the building. Okay, so we require eigenvectors here. So once we calculate the eigenvectors, we can keep it here after solution in the matrix. So so what I need to do, first calculate the weight. So number of beams in X direction are 16 and the length is 7.5 meter. So total length of the beams are calculated as all beam sizes are same, 500 by 400 mm. Number of beams in Y direction are 15, length is 7.5 meter. The number of floors are 15, height of the floor is 4.5 meter, and at ground floor level it is at the first floor level it is 3.5 meter. Number of columns are 20. Okay, at each floor level there are 20 columns. I think you can see it here. I have created a diagram. So 1, 2, 3, 4, 5, 5 by 5, 20 columns on each floor. Okay, there are 20 columns on each floor. So story wise, so there are 16 columns on each 16 beams on each floor, 15 beams on each floor in X and Y direction. So this calculation is floor wise. Okay, each story. Plant dimension 30, 22.5, floor area 13 to 22.5, 675 meters square. Beam size, your column size, thickness of the slab, live load on the slab is 3 kN per meter square. So these are the basic things you need to input. Now I start with the load calculation. What is the dead load? That is the weight of the slab. Okay, the floor area into thickness into density. So floor area I have calculated, thickness is 150 mm and density is 25 for the concrete. Then I have beams along x direction. So length into its volume, that is volume into density. Okay, so length into breadth, breadth into depth into density, that will give me that weight. Okay, into number of beams in x direction and number of beams in y direction, volume into density. Then again columns, volume into density for above floors and for ground floor. Okay, how many 20 columns are there on each floor? So calculation will be for each floor only. Okay, so that is what it is. And above ground floor level, it is this much kilonewton for each floor. So masonry wall, the load on each floor. Then in x direction will be separate, in y direction it will be separate. Okay, because we are calculating load in x and y. So for x and y, the elements in x, that will be the weight. For elements in y, that will be the weight. Okay, so you just need to check infills in x direction, how much weight is there, infills in y direction, how much weight is there. That way you need to add it here. So what is the weight of shear wall in x direction, what is the weight of shear wall in y direction, that also can be added. So this is the dead weight calculation. Here I have not added the floor finish because that was not required for this calculation right now. So live load, floor area into live load into reduction. So whatever is the reduction of your live load as per the IS 875, okay, part 2, that how much live load can be reduced, that you can take from there. So that can also be done. And your seismic weight is calculated. So what is seismic weight? Total weight. So what is the total weight in this live load? That is 25% of the live load plus all dead load. So that will be the seismic weight. Okay. So the live load is taken 25% here and the rest is the dead load. So dead load plus 0.25 of the live load. So that is how it is calculated. Clear. So here you can see weight of the slab, that is same in x and y direction. Masonry wall in x direction, masonry wall in y direction. Okay, so this is slab plus wall, whatever the total is there. This is slab plus wall and this is weight of the slab plus wall, that is total. So this will be how many number of infills are there on each floor and multiply by that. So for the total building we will get the answer. So you basically you want to calculate the total weight and also the floor weight. So floor weight calculation, you add it till bottom at the base of the level, then it will be total weight of the building. So total weight of the building when multiplied by acceleration, you will get base shear. That is the how we calculate in static load, static method. Here what is happening, that we need to calculate floor at each level. Okay, so that will be on roof. There is some weight on story 14. So on each floor we have a seismic weight. That is dead load plus 0.25 times the live load. So that's why it is a floor weight. And from that we calculate the mass participation factor. So it should be more than 65%. Right now I think some error is there. That's why it is showing only 10%. But if it is corrected, then it will show more than 65%. So that is what we had seen in the software. Same we need to calculate it here. So this is very important, mass participation factor and your pk value and mk value. So both need to be calculated. So that is how we do it for mode 1. Similarly for mode 2. So I for mode 3. So if how many modes are there, for all modes so much effort will be required. So if you are creating this Excel, it will take you a lot of time. And after that you can calculate the this one base shear of the building. So it is zone 3, so Z is 0.16, building type is 2, that means here it is important building is type 1, for type 2 it will be importance factor will be 1. Okay, so if it is if I take it as 1, then my importance factor will be 1.5 as per old code. Right now it is 1.2 also. So right now it will be 1, 2, and 3. So if I give 1, it should be 1.5. If I give 2, it should be 1.2. And again, if I give 3, then it will be 1 as per our IS code. So importance factor will be defined by building type. It is important or semi-important or less important. So now time period of the building, again I have given it as 1 for brick infill, 2 without infill. So it is an infill building, so it will take 0.09 h raised to square root of the d. Okay, so that will be how I have programmed it. Height of my building is 67.5 meter. What is my soil type? Either it is rocky soil, or it is a medium soil, or it is a soft soil. So that is 1, 2, and 3. Category 1, 2, and 3. So hard soil, medium soil, soft soil. Based on that, my SA by G value will be estimated. Okay, so based on that, what I will get, I have to take response reduction factor here. So my response reduction factor is 5 for my building. So when I take it 5, my AH value acceleration. So what I need to do is calculate base shear, that is AH into seismic weight. Okay, so this is given as 5. So Z by 2 into I by R into SA by G. So Z by 2 is zone factor divided by 2, 0.24 divided by 2. I is the importance factor, R is the response reduction factor, SA by G depends on your time period. So based on the time period from the code, you will get SA by G. Okay, from response reduction, response spectrum curve. So that also we will see. Okay, so this is about that, and this for mode 1, mode 2, and mode 3. So for all 3 modes you need to calculate AH value. So acceleration for all 3 modes need to be calculated. Okay, now this is the story forces QIK. So at each story how much force will be there. VIK is the base shear. Okay, just a minute, somebody is there in the lobby. Okay. So now base shear we have to calculate. So whatever the story shear is there, okay, if we take that story shear, then QIK factor will be, QIK curve will be there. Now if we add of the top story plus the bottom story, then this type of diagram you will be created. So 15 story plus 14 story, then 15, 14, 13, then 15, 14, 13, 12. So this is how we keep on adding it, then we get base shear. If we take the story shear, then it will be in parabolic pattern in as per the IS code. As per ACI code, it is a triangular loading pattern. As per the Euro code, it is first mode loading pattern. So loading pattern, we have a different session. Okay, so once you start calculating and create an Excel, okay, it will be very fruitful session for you, because software will do then what you will do. So it is basically that you should also understand that what is happening in the software. And that is why we are always focusing on manual analysis rather than the just software analysis. Okay, so this is what I created for mode 1, that is weight into 5ik. This is the eigenvector. From that I calculate the that formula is given here. Formula of the code is entered here. I get the story shear and the base shear. So this base shear is equal to 15 plus 14. This is equal to 15, 14, 13. Similarly, for the ground floor, total story shear is added, so that becomes a base shear. Okay, so that base shear is 11111.51. And for the mode 1, for mode 2 it is 364 kilonewton. For mode 3 it is 15.40 kilonewton. Now what is happening, time period is there, then natural frequency is there, and I want to calculate the total base shear. So I will add using mode the square sum of root square SRSS. Okay, so root of base shear for mode 1 the whole square plus root of base shear the whole square for mode 2 for mode 3. Okay, so whatever base shear I have got, I will square it and add it and root of that. So that answer I will get for each story. So that is the final base shear for your building with 3 modes will be available to you. So this is for story shear, this will be the base shear. Okay, both are very important. So that was with SRSS method. There is second method, that is CQC, in which is a very difficult thing to achieve. You need to create matrix, then you need to solve it for all the story, and finally you get the base shear, that is again equal to 11111. Okay, so if I can get this value, it is 1172.31. So both methods will have some difference, CQC method and SRSS method. The sum of root of square method and CQC method is there, 2 method for modal combination. So we are combining the response of various modes. So mode 1, mode 2, mode 3, we are combining it by SRSS method and or by CQC method. So any method you need to follow, either CQC or SRSS method. CQC method is generally followed when the time period of the building is nearby each other. Okay, so if it is nearby each other in mode 1, mode 2, mode 3, then we follow CQC method. So if it is separated mode 1, mode 2, mode 3 by 10%, then we don't have to follow CQC method, we have to follow SRSS method. Okay, so details regarding that also we will share in the next session. So that was about the dynamic analysis, that is response spectrum method, and the static method of analysis in Etabs, as well as in Excel, that how you can do it for yourself, right? So I think we should end the session here today, so that we can you can try yourself that whatever we have done, you can try with Excel, right? So Subhash, what you have to say for regarding this?
Yes, sir. I'm clear, sir. Clear.
I mean, we need to create an Excel. Will you be able to create it?
Yes, sir. We can make, sir.
Okay, okay. Okay, so try to make an Excel for your own self, because that is the manual analysis, and then we can compare with Etabs, that whatever you are doing on Excel, same or nearby should be in Etabs. Otherwise, the Etabs is wrong. Okay, so that is how we are doing it. Yeah, we will be doing it. The 7-story model, 7-story building. I will be giving a schematic of entire process in this note form. Okay, so I will be drawing the sketch, and I will be making it and sharing it with you. Okay, so so that whatever we have discussed today, that is on paper. Okay. So basically it is understood that we are doing multi-degree of freedom analysis, that is a dynamic analysis and static analysis. Static analysis, we calculate the total weight of the building, multiply with acceleration and calculate base shear. In dynamic analysis, we create mass matrix, stiffness matrix. Okay, and mass is given at each story and stiffness is also at each story. Stiffness in lump mass model is given by columns, shear walls and infills at each story. Okay, so we are talking each story in dynamic analysis and whole building in static analysis. That is the main difference. Okay, so any doubt you have, then you can ask. Anyone has a doubt? Because basically it is a basic session, but still if you have some doubt, then you can ask right now. Okay, so if it is clear, then I will give a schematic and you try to create an Excel for you. So manual analysis using an Excel, so it will be useful to you in your own particular calculations. If you have your own building, you can do it yourself. Okay, so dynamic analysis you need to do in Excel. That will be a very good option. So I will share the formulas, I will share a schematic, and based on that you can try a building. This own building, similar what we have done. So I will share that details also, what is the building. So everything I will give you the input, you can start creating an Excel. That will be helpful to you in longer run. Okay. Okay, so we can end the session today, and just hold on. I will stop the recording so that it is